All right, I think we can probably go ahead and get started at this point. So it's a pleasure today to have Dhruba Dutta Chowdhury joining us to give our lunch talk. Dhruba is a grad student at Yale, where he works with Frank Van den Bosch and Peter Van Dokkum. His research interests focus on understanding the nature of dark matter, so in particular fuzzy dark matter, but he's also worked a lot on understanding ultra-diffuse galaxies, and also done work on the Sunyaev-Zeldovich effect, so quite a broad range of interests. But today he's going to tell us about constraining dark matter using gravitational heating and cooling processes. So, take it away.
Thanks. Thank you, Andrew, for the nice introduction. And thanks for having me give a talk at Carnegie. So let me begin with a brief outline to my talk. So I'll start by introducing what is fuzzy or ultralight dark matter. Then I will talk about gravitational heating and cooling mechanisms in general, just to for people who may not be familiar, and just to sort of introduce the gravitational cooling and heating mechanisms that I am going to be interested in for the purpose of this talk. And then I'm going to specifically talk about sources of heating and cooling in fuzzy dark matter, and what is the impact of those processes on nuclear objects and dwarf galaxies. And then finally, I'm also going to talk about something else. So I'm going to talk about heating and cooling mechanisms in the galaxy NGC 1052 DF2, and what we can learn about the distribution of dark matter in that galaxy using these processes. Okay. So we know that we have ample evidence for the existence of dark matter, but we are still ignorant about some of the basic properties. We still don't know what the nature of dark matter is. We don't know what the mass of the dark matter particle is. And so the mass of dark matter particle can lie anywhere in this sort of range. So it could be a weakly interacting massive particle, which is the most well-motivated candidate for cold dark matter. And this can be the mass can be like 10 to the power 9 to 10 to the power 11 electron volt. However, it could also be an axion. So it could be a QCD axion, in which case the mass would be somewhere here. And other than that, it could also be axion-like particles, which are also well motivated. And in that case, the mass would be 10 to the power minus 22 to minus 20 electron volts. But we do know some things about dark matter. And one of the things that we know is the dark matter density in the solar neighborhood. And that is about 0.4 giga electron volts per centimeter cube. Now, given this information, we can ask this interesting question that at what mass is the average interparticle separation less than the de Broglie wavelength? And by which I mean the Planck's constant by the mass of the dark matter particles and the typical velocity. So this is a cartoon that illustrates the situation. So if we think about this sphere or this circle here as a de Broglie volume, so I'm thinking about a situation where there are many dark matter particles inside this de Broglie volume. And therefore, they have to be bosonic, and that just follows from the Pauli exclusion principle. And turns out that if you do this calculation, assuming a velocity of 200 kilometers per second, which is the standard velocity in the Milky Way, then this mass turns out to be about less than or equal to 30 electron volts. And this is what we call the wave regime. So this is the regime where the dark matter particle would behave as a wave, or dark matter would behave as a wave. And if the mass is very small, so if it's like minus 22 to minus 20 electron volts, then we call it ultralight or fuzzy dark matter. Okay. Now, the investigations of fuzzy dark matter as a dark matter candidate, it's not new. So there's a long history of investigations, and I've just pointed out some papers. But the renewed interest in this kind of models, or for that matter, any alternative dark matter model, let's say self-interacting dark matter, for example, that is because of the so far null detection of WIMPs and no evidence for supersymmetry, the connection between the two being that WIMPs are predicted to exist in supersymmetry. And sort of in the non-relativistic limit, the dynamics of fuzzy dark matter that is governed by the Schrodinger-Poisson equation. So this here, the first equation, that is the well-known Schrodinger equation. So psi is the wave function, phi is the potential, and mb, that is the mass of the bosonic particle. And this potential that is self-consistently derived from the Poisson equation. So this here is the density. So that is the boson mass times the wave function squared. And turns out that if the boson mass is about 10 to the minus 22 electron volts, then the de Broglie wavelength comes out to be about a kiloparsec. And therefore, the wave nature of dark matter, that would have interesting astrophysical implications. And if you're interested, if you find my talk interesting and you would like to know more, I would highly recommend these review papers, like very, very nice review papers. Okay. So now let me sort of briefly introduce the heating and cooling mechanisms that I'm going to be talking about in this talk. So, and to introduce this, I will use the example of cold dark matter, which is sort of like very common or well known to us. So if we think about a cold dark matter halo, which is smooth. So let's think about a Milky Way halo with a smooth potential. And if we just place a test particle in that halo at any radius in a circular orbit, that's just going to keep rotating or keep moving in a circular orbit. And so that is sort of what is shown here. So you place a particle at 8 kiloparsec, and it sort of just stays in that circular orbit. But now, if the potential is clumpy, and we can sort of think about the substructure in Milky Way, we can think about Milky Way subhalos. So if in the presence of the subhalos now, this orbit is going to be perturbed by gravitational encounters with the subhalos. And in this particular study, the substructure, the mass in substructure, that is about 3% of the Milky Way mass, and you can see that this the particle now starts to go out. And if this process of the encounters of the particle with the clumps, if that is dominated by many weak encounters, then it can be treated as a diffusive process. So by which what I mean is that it can be treated in a statistical way using this equation. This is called the diffusion equation. So if you think about an ensemble of particles, then the average change in energy of that ensemble per unit time, that is given by this diffusion coefficient. So this is called the first order diffusion coefficient. So this is the average change in velocity in the parallel direction of motion per unit time. And these are the second order diffusion coefficients. So this is the average change in velocity squared per unit time in the parallel direction. And similarly, average change in velocity squared per unit time in the perpendicular direction. Now, turns out that this coefficient here, the first order diffusion coefficient, that is negative. So this is a drag term, and this causes cooling. Whereas these terms, these are positive terms, and these are what are the heating terms. And this diffusion coefficients, they basically depend on what the mass of the clumps are, what the density distribution of the clumps is, and what is the velocity dispersion of the clumps. And I just want to mention that via this mechanism, MW, like the substructure in Milky Way, that can perturb global clustered orbits, and it can lead to sort of thickening of stellar streams as well. Now, if the particle is not a test particle, if it's a massive object, then it also perturbs the gravitational potential of the host system. And what happens is that there's a response density that is generated, and the back reaction of this response density that causes the object to slow down, resulting in orbital decay. So that is what is shown here. So you see an object here, and there's a response density. So this is a massive object, and it's just shown at one time. And you see the response density that has been generated in the background halo. And this is the over density, this is the under density. And this response density then causes the orbit of the particle to decay over time. And this back reaction is called
Can I ask a quick question? Is this related to, as opposed to identical with, I forget the title. When you have, it is embarrassing.
Dynamical friction.
You know, people, what is it? Yes, thank you. Dynamical friction. Thank you. Somebody's still young. Is this a similar kind of effect, or is it now
similar to what?
Dynamical friction that we always talk about, which just bodies interacting with the stars and
yes. So I am basically
this
trying. Yes, so I am talking about dynamical friction. Yeah.
okay.
So I'm
That
just
is what
yeah.
it is.
So
Okay.
the dynamical friction is the main cooling mechanism that we're interested in. I'm just trying to introduce that for people who may not be familiar.
Got it. Thank you. Sorry.
Yeah. So now if we think about the diffusion picture, then in this diffusion picture now, the heating terms are the same as before, but now we have an extra cooling terms. And so this is the term that was there already. And now we have this extra term to dynamical friction. And sometimes these two terms together are also known as dynamical friction. And that is just a convention of what you want to call it. And basically these heating and cooling processes, they can sort of inform us about the underlying matter distribution. And that is because, as I said, there's diffusion coefficients, they depend on the properties of the background distribution that is causing this heating and cooling processes. Okay. So now I'll go back to fuzzy dark matter. And so what I'm showing is results from a cosmological fuzzy dark matter simulation. And this is sort of the first cosmological fuzzy dark matter simulation that was run. And so this is for a boson mass of 8 times 10 to the minus 23 electron volts. And the first thing that we notice, so here's a comparison between fuzzy dark matter and cold dark matter. And what we notice is that on large scales, the distribution of halos and filaments, that is sort of similar in fuzzy dark matter and cold dark matter. But now, if we zoom in to one of these halos, then we start to see differences. So now what is done here is we zoom into one of these halos, and we see that there are filaments surrounding the halos. And inside the filaments, we see these sort of interference fringes. And I'm going to talk about what causes these. And we also see there are sort of interference patterns inside the halo. And we zoom in further into the halo, then we see there is a very prominent core at the center of the halo. And the simulations are run with the code Gamer, and it uses adaptive mesh refinement to solve the Schrodinger-Poisson equation. And I also use the same code in my work. Okay. So now what I do is I go to this cosmological fuzzy dark matter simulation that I was showing you before, and I take one halo from the Redshift 0 snapshot of that simulation. And this halo is a typical dwarf mass halo. It has a halo mass of about 6.6 times 10 to the 9 solar masses. And I resimulate this halo in isolation. So it's an idealized simulation with nothing else, just this halo. And you see that there are many interesting features in this halo. So first of all, you see this sort of red central nugget here. And that is what we call the soliton. So this is the ground state of the Schrodinger-Poisson equation. And surrounding the soliton, you see that there are fluctuations throughout the halo. And these fluctuations, they arise from the interference between the excited states of the Schrodinger-Poisson equation, which make up this envelope surrounding the halo. And you also sort of see that this red nugget that is moving around here, and I'll also talk about that in detail later on. So now, let's look at what happens.
I'm sorry, could you just tell us what the time scale of the movie we were just looking at was?
So this is a movie over 10 gigayear.
Thank you.
Yeah, so you can see time moving here. Yeah.
So can I ask something else?
This looks like
also,
a speckle image, you know.
Sorry,
Yeah.
could you repeat that again?
Looks like an astronomical speckle image. It's a very similar effect too, I think.
So I'm not actually, I'm not familiar what a speckle image is.
It has to do with the interference caused by propagation of light through the atmosphere inside the seeing disk.
Yes, so this is also basically interference between the different states of Schrodinger-Poisson equation, which is causing these interference patterns.
And I'm curious about why, I usually think that in the center of a galaxy, the baryonic matter dominates and not the dark matter. And yet this seems to be an effect that you're studying.
This is why I'm thinking about a dwarf galaxy. And I mean, so this is basically a dwarf halo. And so dwarf halos are, so first of all, I don't have any, so what I'm showing is a dark matter only simulation without any baryons. But even with baryons, dwarf galaxies are typically dark matter dominated.
Yes, yes, very different.
Okay. So now let's look at the density profile of this halo as a function of time. So what I'm plotting here is the density. So this is the spherically average density of the halo, and it is shown at different times. So that those are different curves here, and they are color coded by the maximum density of the halo. So first of all, we notice that there is this prominent core. And then at some point, the core transitions into an outskirts, and this outskirts is NFW-like. So the reference 1/r³ profile that is shown by this dashed line here. And the other thing that we notice is these oscillations in density. And so basically, when the density is higher, the core radius is smaller, and vice versa. And now just to mention that in this particular simulation, the system that I'm looking at, this has a soliton of mass about 4 times 10 to the 8 solar masses, and the soliton radius that is about 2 kiloparsecs. Now here, the oscillations in the maximum density that is shown, and what is shown below is the power spectrum of these oscillations. So we find that there is a very characteristic frequency, and this frequency actually depends on the density of the central density. And in this particular case, it's about 2 to 5 gigayear inverse. So now another interesting thing, another interesting feature of this halo, as I was trying to point out when we were looking at the movie, is the fact that the soliton also moves around with respect to the halo center of mass. So what is shown here are 4 different time instants. And first of all, the white crosshairs, they denote the center of mass of the halo. And then you see that the soliton that is sort of offset from the center of mass, and this offset keeps changing with time. And the offset as a function of time that is plotted below, and the typical sort of offset or the maximum offset that is about the soliton radius. And again, both these effects, both the oscillation that I was showing previously of the soliton and this motion of the soliton, they happen because of the interference between the ground state, the soliton, and the excited states that surround the soliton. We can also try to characterize the density fluctuations that are there outside the soliton. And this is a very busy plot, but I'll try to sort of explain what I'm showing here. So the way to characterize these density fluctuations is we can sort of go to a particular radius from the center of the soliton, and we can sort of look at the over density as a function of theta phi with respect to the average density at that radius. And then what we can do is we can take the Fourier, or we can take the spherical harmonics expansion of that over density field and get the multipole components. So that is what is shown on the left here. So as a function, so at a given radius and L, so basically as a function of R and L, the angular wave number, the time averaged multipole components are plotted. So we do this at different instants of time, and then we take the average of the multipole components. And so first of all, what we notice is that there is very little power inside. Okay, so there are these two vertical lines here. One is the core radius of the soliton. So the core radius is the radius where the density of the soliton that drops to about half its maximum density. And this is the soliton radius, which is typically sort of the radius where the soliton transitions to the halo. And so the first thing that we notice is inside the core, there is very little power. And so basically, what it means is that the soliton core that is spherically symmetric. And then as we go from the core to the soliton radius, now we see power at low L's. We see power at L equal to 1, 2. And that basically means that the soliton is not really spherical. So we see increasing asphericity going from the core to the soliton radius. Now, outside the soliton radius, now we are now looking at the fluctuations in the halo. And the first thing that we can do is we can sort of pick out the L at a given radius. We can pick out the angular wave number, which has the maximum power, and we can plot that as a function of R. So that is what this pink line here shows, the sort of the jagged pink line. So, and then we can also try to convert the there's a relation between the angular wave number and the physical size of the fluctuation. So if d is, or is the diameter of the fluctuations, then that is related to the angular wave number by this relation, where r is the radius of the sphere over where we are looking at these fluctuations. And so then the next thing that we can do is we can plot this r versus L relation for different values of d. So that is what is shown by this cyan lines here. So they are the RL relation for fixed diameter. So for soliton size, 1.5 times soliton size and 2 times soliton size. So then now if we follow this pink curve, what we see is that the typical size of the fluctuations, they sort of increase from soliton size to about 2 times soliton size. And on the right, what is shown is we can sort of sum over these different components, and we can then find the variance as a function of radius. And so just that variance is plotted. And so the one thing that I want to point out is outside the soliton, there is about order unity variance sort of everywhere throughout the halo. Okay. And then so the final thing in this plot that we can also do is we can compare these what we get from these simulations to some analytical models. So there are these models which say that outside the soliton, we can treat the field or the halo, the fluctuations, as a field of quasi-particles. And the mass of these quasi-particles, they depend on the average density of the halo, and they also depend on the de Broglie wavelength, where the de Broglie wavelength is just h over the boson mass and the Jeans dispersion of the halo. And so once we know what the effective mass is in these models, then we can convert that to a size. We can just assume that, let's say, these quasi-particles are spherical, and we can convert that to a size. We can convert that size to a L using this relation. And that is what is shown by this magenta curve here. So basically, just to show that the typical fluctuation size outside the soliton that is inferred from our simulations, that agrees with this analytical quasi-particle based picture. Okay. So now, so therefore, there are these different sources of heating in a fuzzy dark matter halo, or different sources of gravitational potential fluctuations. So one is the fact that the soliton is moving around. Then the second is the fact that there are density oscillations in the soliton. And the third are these density fluctuations outside the halo. And together, what they do is, so if you sort of put something at the center of the soliton, and we can think of it as a black hole or a nuclear star cluster that is at the center, supposed to be at the center of the potential well, but because of these potential fluctuations or sources of heating, what happens is that this object will sort of keep moving out over time. And that is what is shown in this movie. So we place, and in this particular case, I'm showing the motion of a 10⁵ solar mass particle, which is placed at the center of the soliton, and then it just sort of keeps moving out over time. Below, what is shown is the motion of this particle with respect to the halo center of mass and with respect to the soliton center. They're not exactly the same because the soliton is moving around with respect to the halo center of mass. And that reference motion, the motion of the soliton with respect to the halo center of mass, that is also plotted with this blue line. Now, how long will this motion continue? So basically, this motion will continue until there's a force of dynamical friction that is able to balance the heating. And when the dynamical friction becomes important, that depends on the mass of the particle. So therefore, then this outward motion that will continue as long as, in a sort of ensemble average sense, the heating and cooling rates are able to balance each other. So that is what we look at next. So we make ensembles of different mass particles. So starting from 10⁵ to 10⁶ to 5 times 10⁶ to 10⁷ solar mass particles. And for these different ensembles, what we look at, so then the way these ensembles are created is by putting the particle at the center of the soliton at different instants of time. And what is plotted here is the evolution of the average radius, or rather the mean. So it is the median radius of these ensembles and the 16 to 84 percentiles. And in each case, we also compare it with an ensemble of massless particles. So basically we put 0 mass particles and see what happens to them. And the results for the massless particles, they are shown in cyan. So now if we go from top to bottom, what we see is that the motion of 10 to the power 5 and 10 to the power 6 solar mass particles, that is almost identical or exactly the same as massless particles. And so basically what this means is that dynamical friction for these masses, they become important at much later radii, and we just don't reach those distances in 20 gigayear. And for the simulation time that we examine, dynamical friction is insignificant on these masses. But now if we start increasing the mass, we go to 5 times 10 to the power 6. So now we start seeing the effect of dynamical friction. So compared to massless particles, we see a reduced rate of outward diffusion. And finally, if we go to 10 to the power 7 solar mass particles, then we also sort of see kind of a stalling behavior. So this is what you would expect if the heating and cooling processes are trying to balance each other. So in an average sense, there is no further outward motion. Okay. So now I just want to mention that in previous work that has looked at this motion of star clusters or motion of black holes in a fuzzy dark matter halo, that has mostly looked at the motion that would happen as a result of the interactions of these as a result of the interactions with the halo fluctuations, and it has been done using these diffusion coefficients. Now, that is a fair thing to do as long as we are interested in what happens because of the halo density fluctuations. But then if you're interested in the interactions of the particle with the soliton, and that will dominate if the particle is near the soliton or inside the soliton, then we can't really treat it in a diffusion picture, because the soliton sort of acts as a single body which is interacting with these particles. And therefore, that sort of necessitates or sort of sets our work apart. Therefore, we do need this kind of simulation to sort of understand what will happen inside the soliton or close to the soliton. Okay. So now, what do we find in observation? So therefore, we have this prediction of what happens to a nuclear object when in a fuzzy dark matter halo. And what do we see in observations? So I'm showing you two results. One is from a recent sample of dwarf galaxies. And so in the red crosshairs, they show black holes, and the black holes are detected in radio in these dwarf galaxies. And what you also see in the background is the galaxy itself. Now, what you find is that the black holes are actually offset from the center of the halo or the center of the galaxy. And I'm showing you 4 examples, but in this particular sample, what the authors say is that most of their galaxies actually have off-centered black holes. And what I'm also showing is a sample of nucleated galaxies, and these are sort of off-centered nuclear star clusters in the sample of MATLAS dwarfs. So these are dwarfs in the outskirts of the Virgo cluster. And again, we find that sort of the nuclear star clusters can actually have offsets, and the offset is characterized as a function. So it's divided by the galaxy radius and characterizes the function of the surface brightness and the Sersic index of the galaxy. Now, these offsets may not have to do anything with dark matter. These offsets could be because of baryonic physics. It could be related to sort of gas inflows, and also could happen because of mergers, two galaxies merging together. But then it could also have to do with the underlying dark matter physics. And so therefore, if you want to use these offsets sort of constrain the boson mass, what we need to do is first predict these offsets as a function of halo and boson mass. And then we can sort of use this to sort of rule out or constrain fuzzy dark matter. And we leave that for future work. And what I'm going to show you next is what happens to a dwarf galaxy in a fuzzy dark matter halo. And this is work in preparation. So, and some of you might already be wondering about this, that okay, if we have this nuclear objects and they sort of start moving out in a fuzzy dark matter halo, then what would happen to a dwarf galaxy in fuzzy dark matter? And we also wondered about it. And so what we do is that we take the time, so the potential of the halo that is fluctuating, but then we can sort of look at the time average potential, and we can set up a galaxy in equilibrium with the time average potential. And so we set up a 10 to the 6 solar mass galaxy, and it has an initial radius of about 0.7 kiloparsec. So we are thinking about Fornax in this particular case. Although Fornax has a higher mass, but sort of the typical sizes of the dwarf galaxies, they sort of, at least the classical dwarfs, they range from, I think, 0.2 to 0.7 kiloparsec. That's why we set up a galaxy like this. And then what we find is that the galaxy sort of expands over time. So there are these heating mechanisms that are operating, and they just keep, so the galaxy just keeps puffing up. So what is shown here is the half light radius or the half mass radius of the galaxy. And in sort of 10 giga-year, the half mass radius that increases by a factor of 5. And what is shown also is the maximum density, or so the peak density of the galaxy, and that decreases by more than a factor of 10 over 10 giga-year. So therefore, there's another sort of prediction in fuzzy dark matter, and that would be a correlation between galaxy size and age. So older galaxies will tend to be more diffuse, and that's also, therefore we can also sort of try to think about constraining fuzzy dark matter using sort of sizes of dwarf galaxies. But so two words of caution. One is that here we are looking at an isolated system. So we have isolated halo, and we simulate the evolution of the dwarf in that. But in order to sort of really do this carefully, what we all need to sort of look at is the cosmological assembly history of the halo, because as the halo will assemble, its mass will change, the properties of the solid on the halo will change, and the heating effect will change. And in addition, if you want to use the Milky Way dwarfs, or for that, I mean, if you want to use satellite galaxies, then we would also have to think about what happens because of the field of the host halo. And it has been shown that in the tidal field of the Milky Way, what will happen? So if we have a fuzzy dark matter halo in the tidal field of the Milky Way, then as the halo keeps stripping, the random walk of the soliton that decreases. And I'll try to show later that most of this heating is actually dominated by the random walk, and therefore the heating mechanism will also decrease. So therefore, we need to do more detailed modeling in order to use these to constrain the fuzzy dark matter particle mass. So now let me talk about sort of a semi-analytical model that we have been trying to build to sort of predict this heating in fuzzy dark matter halos. So this model has sort of different components. So we know that there are at least 3 important mechanisms, and we try to model them separately. And so the idea is that if we can sort of have them separately, we can turn on, turn off these knobs and sort of look at what happens individually with these different components. So first of all, we model the background halo. So there is the soliton and there is the halo. So we model the envelope or the background as a fixed non-oscillating structure, and we model that as a core NFW halo. So that is what is shown by the black curve. So for some reason, I don't have my cursor. And then we model the Soliton oscillations as a single frequency sinusoid. So if you remember, when I was talking about the Soliton oscillations, I showed you the plot. There was sort of a very characteristic frequency, and we can at first order, we can sort of say that, okay, let's model them as a single frequency sinusoidal oscillation. So that is what we do. So the peak density varies with the sine wave, and then we set the soliton size following mass conservation. And we also assume that the soliton remains spherical with its sort of characteristic profile. So in cosmological simulations, it is seen that the sort of time average soliton profile that is given by the relation that I'm showing below. And we assume that when the soliton is oscillating, that relation is also maintained. So now then from the simulations, we know how the soliton is moving around. So we know what the random walk is. And we just take that as we see in the simulation and input that in our semi-analytical model. And finally, the effect of the envelope density fluctuations that is modeled using the diffusion coefficients that I was talking about. So in this quasi-particle picture. And I can talk about that later in more detail if people are interested, how this is done. Okay, so now let's see component by component what happens. Let's build on these components one by one and see what happens. So first of all, let's think about a situation where the soliton is only oscillating and nothing else is happening. So we have a background halo which is fixed and the soliton is oscillating. So we find that the soliton oscillations by themselves, they don't do much. So in black, the results of the simulation is shown, So this is the half-light radius and the maximum density of the galaxy. And then in red is what happens if we just have oscillations and nothing else. And sort of the reason why the oscillations don't do much, that has to do with sort of the time scales for the oscillations and the typical time scales of orbits inside the galaxy. So what is plotted here on the y-axis is the ratio of the oscillation time scale divided by circular orbital time scales as a function of radius, which is on the x-axis. And we find that most of the galaxy, about 75% of the galaxy mass, that sort of lies in this region where it's adiabatic. So the oscillation time scale that is greater than the orbital time scale. So basically, therefore, soliton oscillations, they're largely adiabatic. And that is the reason why by themselves, they don't do much. So now let's turn on the other knobs and see what happens. So now we have a fixed background halo. And now we just move around the soliton and do nothing else. So it's not oscillating. We don't add any contribution from the fluctuations in the halo. So we see that we get some heating, substantial amount of heating, but it's below what we see in the simulations. So now let's add on the effect of the oscillation. So now we have a soliton that is moving around and a soliton that is also oscillating. So we get more heating now, and we are closer to what is seen in the simulations. And finally, let's add the effect of these quasi-particles or the density fluctuations. So I would sort of argue that our component by component model that works reasonably well, we shouldn't expect exactly the same as we see in the simulations because it is an approximate model. And sort of the upshot is that the heating is dominated by the soliton random walk, at least in this halo and boson mass that we have looked at. And there is also scope for improvement in this model. And the main improvement is by taking account the asphericity of the soliton. We know that the soliton is not spherical, but we have assumed it's spherical. So if we make it aspherical, maybe we'll have some more heating, some extra heating, at least in the inner regions. Okay. So some of the future work that I'm interested in the context of fuzzy dark matter is to sort of quantify this soliton random walk and oscillations as a function of halo mass and boson mass using simulations, which still remains to be done, and then sort of predict offsets for nuclear objects as a function of halo and boson mass, contrast this with CDM. And why contrasting with CDM is important is because it has been shown that if you have a cold dark matter halo, then inside a cold halo, there is also dynamical heating mechanisms that operate, and they can sort of kick out massive objects. So it's something opposite to dynamical friction that happens inside the core, and they can sort of kick out massive objects to at least the core radius. So therefore, it is important to compare these and also compare with observations. And we can improve our semi-analytical heating model. And then we can also use this model to make these predictions, and that would allow a much more elaborate and quicker exploration of the parameter space. And finally, I'm also interested in sort of predicting galaxy sizes, central densities in fuzzy dark matter. And as I said, that we need to do this in a cosmological setting, and we can do this using hydro simulations or semi-analytical galaxy formation models. We can try to sort of adapt semi-analytical galaxy formation models to fuzzy dark matter and compare with observations. So now I will stop talking about fuzzy dark matter. And so the remaining time that I have, I will talk about this galaxy NGC 1052 DF2 and sort of look at the heating and cooling mechanisms in this galaxy. So this is a galaxy that is in the NGC 1052 group, and this is at a distance of 20 kiloparsecs. It is an ultra diffuse galaxy. So its size is 2.2 kiloparsec. And so the surface brightness is slightly above 24 Mach per arc second square. And one important thing that will become important later is that this galaxy has a cored stellar profile, and it has about 10 spectroscopically confirmed globular clusters, which is sort of anomalous for these stellar masses. And the other interesting or anomalous things about this galaxy is, first of all, its luminosity function. So its luminosity function is shifted to higher magnitudes compared to typical sort of other galaxies. So if we look at so the histogram here, that shows the luminosity function of the globular clusters in this galaxy, and then it is compared to sort of typical luminosity functions that we observe for Milky Way like galaxies, or even in the coma ultra diffuse galaxies, and it is offset to higher magnitudes. And the other thing that is anomalous is its dynamical mass. So, and the dynamical mass has been measured using the kinematics of the globular clusters and also using the kinematics of the stars. And given the dispersion, we can convert that to sort of a mass using some relations. And the mass constraints from the stellar kinematics and the globular cluster kinematics. Those are shown here. And what is also shown is the different mass profiles. So first of all, a stars only profile. So assuming there is no dark matter, and then also two different dark matter halos. One is the 10⁹ solar mass dark matter halo with a cusp, and then other is the 10⁹ solar mass dark matter halo with a core. So the kinematics of the stars and the globular clusters, they are consistent with the absence of dark matter, but then they can sort of also allow for a low mass up to about 5 times the total stellar mass dark matter halo. So then the question is sort of, can we learn something more about dark matter using sort of the dynamics of the globular clusters? So basically we ask sort of these 3 important questions. One is sort of how quickly do the globular clusters spiral into the galaxy center in a baryon-only model? What happens if we add a dark matter halo? And then are globular mergers important? So and the reason we're thinking about mergers is because there are these 10 globular clusters, and there's also another reason which I will tell you later. And if mergers are relevant, then can they explain the anomalous luminosity function of the globular clusters? And we answer these questions using n-body simulations and analytical and semi-analytical model. Okay, so let's first put one globular cluster and see what happens. So what is shown on the left is the data for these globular clusters. You see the projected image of the galaxy, and you see the different 10 globular clusters. So what we do is we make a model, and the galaxy model that is consistent with observation. So we know what the projected density is. We can assume that the galaxy is spherical, and we can set up particles. We can obtain the distribution function. I'm not going to details of how that is done, but we can sort of set up particles, give them velocities and positions to have our galaxy model. And then we also know the projected positions of the globular clusters and the line of sight velocities of the globular clusters. We can also use those as constraints. And then we also have a distribution function for the globular clusters. And from that, we can draw the other 3 phase space coordinates of the globular clusters, and we can put them and then evolve it over time. So first of all, let's see what happens if we have one globular cluster. So let's take just one of them. So then what we, and since there is this uncertainty in the other 3 phase space coordinates of the globular clusters, so basically what we find is there is a large realization to realization variance in the evolution of the globular clusters. So what is shown here is the radial evolution of the globular clusters, the angular momentum evolution, and the energy evolution. So first thing to note is the realization to realization variance. Depending on what we pick for the other 3 phase space coordinates, we can get significant variance. And the other very important or interesting thing is that so we see that the orbit decays because of dynamical friction, and then at some point sort of the decay stops and we sort of have this saturation, and this is known as core stalling, and that's why the core profile of the galaxy is important. And the reason core stalling happens, that has been sort of investigated before also with simulations as well as analytical trying to explain it analytically. And sort of the reason behind that is there are 2 reasons. One is there is this dynamical friction picture where resonances are responsible for dynamical friction, and it has been shown that in a cored galaxy near the core, the number and strength of these resonances, they decrease. So that therefore you have a decreased dynamical friction. And then the other thing that is important is we actually have a heating. So the direction of the torque actually reverses inside the core. And so there's actually a dynamical heating inside the core, and that can sort of, that pushes things outwards. And together sort of what they do is you have this core stalling. And so that's why, as I said, that in cored dark matter halos, the dynamical heating mechanism is important, and that needs to be contrasted with fuzzy dark matter. Okay, so now let's put all the 10 globular clusters together and see what happens. So there's a movie that shows that, and here's the evolution, the radial evolution and the angular momentum evolution of the 10 globular clusters. So in addition to core stalling, the other sort of thing that happens is there is this interaction between the globular clusters. You can sort of see it here. For example, this red the red one and the blue one, they're sort of interacting with each other. So there is significant orbital evolution. Some of the globular clusters, the more massive ones, they do evolve quite a bit. However, there is this interaction between the globular clusters, and there is also core stalling. And together, what these do is that they will prevent the globular clusters from sinking to the center of the galaxy. So they will sort of keep them bound, the core stalling as well as the globular interactions. So we can also look at what happens to the half number radius of the globular clusters as a function of time, and the dispersion of the globular cluster system as a function of time. And we see that the half-light radius does evolve, and it evolves by about 50% in 10 gigayear. So the globular cluster system does become more compact. But then what happens when you add dark matter? And this we didn't do with simulation. So what we used instead was some semi-analytical modeling, semi-analytical prescriptions for dynamical friction. So these are the three different mass models, if you remember. One is a model with no dark matter, and then there is a core dark matter model, and there is also a cuspy dark matter model. And we can look at sort of the dynamical friction time scales in these three different models. So we look at typical time scales for a typical DF2 globular cluster, which has a mass of about 10 to the 6 solar masses on a circular orbit. And we see that if it's a model with no dark matter, if it's a cored galaxy, then we sort of see this core stalling behavior. And then if there is dark matter, then if it's a cuspy halo, in a cuspy halo, there is no core stalling. And actually the dynamical friction timescales, they are much shorter inside, say, 0.3 or 0.4 RE. Dynamical friction timescales are much shorter. So globular clusters in this region would actually sink in much more quickly compared to a Baryon-Only model, where you would see this sort of stalling. And finally, if you have a core dark matter halo, a core dark matter halo can also cause stalling. And that will happen, that will depend upon what the core size is. In this particular case, the core size that we had was a bit smaller than the dark matter, than the stellar core, and therefore we see stalling at a smaller radius. Because of the significantly shorter time scales, inspiral time scales in a cuspy dark matter halo, we can at least say that it's very improbable for the galaxy to have a dark matter cusp, because if it had a dark matter cusp, then the globular cluster central region, they would have sort of quickly sunk to the center and would have created a nuclear star cluster. And we don't observe that. The globular clusters are sort of 10 gigayear old, and the galaxy doesn't have a nuclear star cluster. So we think that it is much more likely that the galaxy either has no dark matter, or even if it has dark matter, then the dark matter distribution must be a core dark matter distribution. So finally, in the remaining sort of, I think, 5 minutes, I'll just point out another interesting study with mergers. So as I said, so there are these 10 globular clusters, and merger between the globular clusters might be important, because if you look at the internal dispersions of the globular clusters, this is what is shown here, and this is not measured. So we have the measured masses and the projected radii, and we can sort of infer the dispersions of the globular clusters, the internal ones. And if we compare that to the dispersion of the globular cluster system, and a histogram is shown here because we have this sort of 50 realizations, and the histogram of the dispersion of the globular cluster system over these 50 realizations is shown. And what you see is that the internal dispersions, they're comparable to the dispersion of the globular cluster system. And this is sort of the regime when mergers could be important. And therefore, we looked at this. We looked at this with live globular cluster simulations. All the previous results I showed you, they were with point particles. We were modeling the globular clusters as point particles. So then what we did was that we chose some of those simulations, and then we replaced our point particles by live globular clusters. And this is just to show the enormous range of scales and densities that we resolve with these live globular cluster simulations. And sort of the upshot that we found was that mergers are actually very rare. And we did this with simulations, and we also calculated the merger rate analytically. And sort of the main reason behind why mergers are rare is because, given the number density of the globular clusters and sort of the sizes of the globular clusters, if you do the calculation, you'll see that the merger rate turns out to be low. And therefore, we think that the globular mergers, they cannot explain the anomalous luminosity function of the globular clusters. The only case where they could explain it is if the galaxy sort of started out with a much more richer population of globular clusters. So if it had, like, say, 100 globular clusters to begin with, at least a factor of 10 larger, which seems a bit unlikely, because, I mean, the globular cluster population currently observed is already anomalous. So therefore, mergers probably are not important. in shaping the luminosity function on the globular cluster. So I'll stop here, and I'll leave you with my summary, and I will take questions.
Great, thank you, Dhruba. We have time for a few questions. Let's see, Steve, you have one?
Yeah, I have a couple of questions. One is, in the simulation where the stellar density expands because of the excitation from the fuzzy dark matter soliton thing, where does the energy come from?
So, I mean, energy of the soliton and so the energy of the halo and the energy ultimately comes from the halo. So, I mean, the halo basically, or the soliton and the halo density fluctuations, so they will transfer energy to the system of stars.
I understand, but then is the halo is the fuzzy dark matter halo contracting to compensate?
It should, if the so if we keep increasing the mass of the galaxy, then at some point we should see that. But since we are sort of thinking about the galaxy mass was very like a very, so we put a 10 to the power 6 solar mass galaxy in sort of a 10 to the power 10 solar mass halo, but we have also done it 10 to a 7 solar mass galaxy. So basically, since the system is dark matter dominated, we can sort of think that the galaxy is behaving as a test.
I understand.
System.
So you're just saying that it's so dark matter dominated that the change in energy of the dark matter.
So it's so dark matter dominated that the change in energy of the dark matter system, that should not be visible, or should be very hard to sort of see.
Okay, the second question that I have is, have you considered whether the density fluctuations caused by the sort of that interference effect in outside of the soliton has a significant effect in gravitational lensing? And
So
the propagation
no,
of light through that very model-y type of density distribution must be very curious.
So that is definitely one interesting. So no, we haven't yet looked at implications for gravitational lensing. But yes, that is something definitely interesting to look at.
Thank you.
Let's see, Ethan, you had a question?
Yeah, thanks for this talk. I was also wondering about the dwarf galaxy expansion. And I guess what I'm wondering is, like, for systems at fixed stellar mass that are observed to have very different sizes. So I'm thinking of, like, Antlia 2 versus maybe like Draco or something. How sensitive is the size expansion to, like, the halo properties? In other words, like, is it more sensitive to halo mass and concentration than we expect the scatter to be at fixed stellar mass anyway? So can this effectively, like, increase how significantly does this mechanism increase the diversity of dwarf galaxy properties relative to just the scatter we would otherwise expect?
So it remains to be, so as I said, it remains to be investigated. It should be very sensitive to the dark matter properties, because as you change the dark matter halo mass, the soliton mass changes, the soliton size changes. So basically, if you increase the dark matter halo mass, then the size of the soliton decreases, and vice versa. So therefore, the heating mechanisms that would change. And then, as I also said, that if you're thinking about Milky Way satellites, then you need to also think about tidal effects. They will also sort of change the profile of the soliton, profile of the halo. That will also change the heating effect. So to summarize, it remains to be investigated that if these effects, they can sort of create more diversity in the dwarf population, or even if they can sort of reproduce what we observe for the dwarf population. I mean, I think if you make the boson mass too small, then your galaxies are going to be just way too larger than what we observe. So maybe we'll not be able to reproduce the sizes of the ultrafaints unless the ultrafaints are all living in sort of halos which have been totally stripped, and they are just solitons. So that's why this heating effect doesn't operate on them.
Makes sense. Thank you.
All right, Xiaolong, you have a question?
Yeah, so very interesting talk. So I have basically two questions. So one is that, so if we consider one particle moving through the fluctuating density, then does the
Sorry, can you repeat your question? I'm not
yes,
sure
so my question is that, so if we consider one particles moving through some fluctuating gravitational potential, does the velocity of the particle relevant for the effect you consider?
So if we consider a particle moving through
moving through the rapidly changing potential caused by the interference. So does the velocity of the particle is relevant?
In addition to, so you're saying in addition to mass, is the velocity of the particle also relevant?
So
I mean,
I would think,
I would think.
Okay,
yeah, sorry, go ahead.
So for example, if we consider that these particles moving through some potential and the potential is changing. So if the particle pass through this potential is the time scale is like smaller or larger than the time scale that this potential changing, it seems that
that's a very good point. Yeah, that's a very good point. So if it's moving on a time scale, yeah, so it should, yeah. So that is basically the reason why we see that the Soliton oscillations don't do anything, because the time scale for the Soliton oscillations are larger compared to the time scale for the motion of the particles. But so that the random walk, that sort of has a very broad power spectrum, and so it has power at all frequencies. So the random walk therefore is more sensitive to a broader velocity distribution for the particles. But yes, I mean, definitely it should depend on the velocity of the particles.
So and then this leads to my second question. So in so I think you show the plot that this so if for the massless particles in the FDM halo, its orbital radius keep increasing. So I'm wondering in this case, which is the most important effect? So like it's I just said, it's the random motion of the soliton or the oscillation of the soliton of the surrounding part. So which one you think is the most
that's
important?
what I was trying to show with the semi-analytical model. So I would say that at least for the halo mass and boson mass that we have studied, we find that the random walk is dominant over the other two components, as I showed in the semi-analytical model. But now when we go to different halo masses, different boson masses, it still remains to be quantified. The random walk itself remains to be quantified. So it remains to be seen that whether it's always the random walk that dominates, or are there certain scales, certain halo mass, boson mass combinations where the oscillations could dominate, or the density fluctuations could dominate. So it remains to be seen.
Okay. Yeah, so that also means that, so if we, so as you said, if we consider also the tidal stripping, that may also have some important effect. So yeah. Okay, thanks. Yeah.
All right, do we have any more questions? Not seeing any. So in that case, let's thank Dhruba again for a really interesting, really nice presentation. And thanks everyone else for joining us.
Thank you very much.
Thank you.
Very good. Thank you.
Thank you for having me. Yeah, thanks everyone for listening to the talk.
Absolutely. Really nice, really interesting work.
Thanks.
Thanks.